Now, let us consider another problem as per which there is an LTI system to which an input of 1, comma 1 is given and the output obtained for the same is y of n is equal to 1, comma 2, comma 1. We need to find the impulse response h of n of the LTI system. For the given x of n, the Z transform can be obtained as x of z is equal to 1 plus z inverse. Similarly, the Z transform of y of n can be obtained as y of z is equal to 1 plus 2z inverse plus z power minus 2. This can be simplified as 1 plus z inverse whole square. From this, the system function of the LTI system can be written as h of z is equal to y of z by x of z, which becomes 1 plus z inverse. So from the definition of Z transform, the impulse response can be written as h of n is equal to 1 comma 1, where the first one corresponds to the instant n is equal to 0. So this is the impulse response of the LTI system. Now let us consider another problem in which there is a LTI system which is described by the difference equation y of n minus a1 y of n minus 1 equal to b0 into x of n plus b1 into x of n minus 1. It's given that the system is causal and unstable. It's also given that a1 is greater than 0 and b0 and b1 are such that there is no pole 0 cancellation and both of them are positive. We need to find the required condition that needs to be satisfied from the given data. So by taking Z transform on both sides for the given difference equation, we get that y of z minus a1 z inverse y of z is equal to b0 x of z plus b1 z inverse x of z. Therefore, the system function of the LTI system becomes h of z is equal to y of z by x of z is equal to b0 plus b1 z inverse divided by 1 minus a1 z inverse. From this, we see that the possible ROCs are mod z greater than mod a1 and mod z less than a1. Please note that a1 is positive. If mod z, but it is given that the system is causal and unstable, so mod z less than a1 is not a possible ROC. So from as the system is causal, mod z greater than a1 is the possible ROC. As the system is unstable, a1 should be greater than 1 because in this case the ROC wouldn't include the unit circle. From this, we see that the condition that needs to be satisfied is a1 greater than 1. Now, let us consider another problem as per which the system function of a LTI system is given as h of z is equal to z inverse minus 3 phase 30 degrees divided by 1 minus 3 phase 30 degrees z inverse. It's given that the system is stable. Then what is the condition that needs to be satisfied out of the options given? That is, the system is causal, the system is anti-causal, and the system is memoryless, and the system is non-causal but not anti-causal. From this, we see that if the system is stable, we have to pick the condition that needs to be satisfied. For the given LTI system, the possible ROCs are mod z greater than 3 and mod z less than 3. So in case of the first ROC, the system is causal and unstable. In case of second ROC, the system is causal, sorry, the system is stable, anti-causal, and non-causal. From this, we see that if the system is stable, it implies that the system is anti-causal. So the correct option is B. Now, let us consider another problem as per which there is a signal x of n which has the z transform as x of z is equal to sigma k equal to minus infinity to plus infinity 2 power 2k plus 1 multiplied by z power minus 2k plus 1. So here we need to find the signal to which the x of n is orthogonal to out of the options given. Option A corresponds to sigma k equal to 0 to infinity 2 power minus k multiplied by z power minus k. In case of option B, y of z is sorry, the system function is the z transform is 2z plus 3z inverse. In case of C, the z transform is sigma k equal to minus infinity to plus infinity 2 power 2 minus k z power minus k. In case of D, the z transform is sigma k equal to minus infinity to plus infinity 2 power minus 2k z power minus 2k. Here we see that the coefficients of z power m are positive for x of z and also they are positive for all the options. Also we see that x of n is present at odd instants. In case of option D, the signal is present at even instants. So sigma x of n y star n would be equal to 0 in case of option D. From this we can say that the signal in option D is orthogonal to x of n. So D is the correct option. Now let us consider another problem as per which the system function of a LTI system is given as h of z is equal to 1 plus 3z inverse divided by 1 minus 5 by 8 z inverse plus 1 by 16 z power minus 2. Consider the following statements as related to the above system function. The system is stable for ROC mod z greater than half. The system is non-causal but not anti-causal for ROC 1 by 8 less than mod z less than 2. As per as per statement 3, the system is anti-causal and unstable for ROC mod z less than 1 by 8. We have to pick the correct option out of these three statements. Sorry, we have to find which of the above statements are correct. We know that the system function h of z can be simplified as 1 plus 3z inverse divided by 1 minus 1 by 8 z inverse multiplied by 1 minus 1 by 2 z inverse. From this we see that the possible ROCs are mod z greater than half, 1 by 8 less than mod z less than half, and mod z less than 1 by 8. From this we see that in case of the first ROC, the system is stable and causal, so the statement 1 is correct. In case of second ROC, we see that the system is unstable and non-causal and not anti-causal. but the ROC given in the system statement 2 is not correct, as ROC is not bounded by poles in this case. In case of the third ROC mod z less than 1 by 8, we see that the system is anti-causal and unstable. From this, we see that the statement 3 are correct. Statement 3 is correct. So we can say that for the given system function, the statements 1 and 3 are correct, but the statement 2 is not correct. Now let us consider another problem, as per which there is a LTI system which is represented by the LCCDE y of n minus a into y of n minus 1 is equal to b into x of n minus 1. It's given that the system is causal and stable. We need to find the condition that needs to be satisfied for the same. From the given LCCDE, we can write the system function as h of z is equal to y of z by x of z is equal to b z inverse divided by 1 minus a z inverse. This is by taking z transform on both sides of LCCDE. So here we see that the ROCs possible are mod z greater than mod a and mod z less than mod a. But we see that the ROC mod z less than mod a is not correct, because of the is not the required one, because of the reason that the system would be anti-causal in this case. So mod z greater than mod a is a correct ROC, but for the system to be stable in this case, mod a should be less than 1. From this we see that the ROC which satisfies the given conditions is mod a less than 1. So this is the required condition. Now let us consider another problem, as per which there is a signal x of n whose z transform is given as x of z is equal to 1 by 1 minus 2z inverse multiplied by 1 minus 3z inverse. We have to find which of the options surely doesn't correspond to the ROC of x of z. The options given are mod z greater than 3, mod z less than 2, 2 less than, mod z less than 4, and none of these. We know that the ROC should be bounded by poles and shouldn't contain any poles. From this, we can say that the possible ROCs of x of z are mod z greater than 3, mod z less than 2, and 2 less than, mod z less than 3. From this, we see that option C doesn't correspond to the ROC of x of z. So the correct option is C. Now let us look into another problem, as per which there is a signal x of n whose z transform is given as x of z is equal to z square minus z inverse plus z power minus 3. It is passed through a LTI system of impulse response h of n is equal to 1 by 3 multiplied by delta of n minus 2. We have to find the output of the LTI system at n is equal to 3. So from the given data, the input to the LTI system has a z transform of x of z is equal to z square minus z inverse plus z power minus 3, and the the system has a system function of 1 by 3 into z power minus 2. From this, the output of the LTI system can be written as y of z is equal to h of z multiplied by x of z, which is equal to 1 by 3 minus 1 by 3 z power minus 3 plus 1 by 3 z power minus 5. So the output of the LTI system y of n at n equal to 3 is the coefficient of z power minus 3, which is minus 1 by 3. So the required answer is minus 1 by 3. Now let us consider another problem, as per which it is given that there is a system function h of z is equal to 1 minus z power minus 6 divided by 1 minus z power minus 1. There are two statements given as related to the system function. The first one is that the system is a FIR filter. The second statement is that the ROC of h of z is mod z greater than 2, 0. We have to find which of these statements is correct. From the given data, the system function can be written as h of z is equal to 1 minus z power minus 3, 1 plus z power minus 3 multiplied by 1 minus z inverse multiplied by 1 plus z power minus 1 plus z power minus 2 divided by 1 minus z power minus 1. So, upon simplification, the h of z can be written as 1 plus z inverse plus z power minus 2 plus z power minus 3 plus z power minus 4 plus z power minus 5. From this, we can say that the filter is a FIR filter because the length of the impulse response is finite. Also, the summation in h of z will be finite only if mod z is not equal to 0. From this, we can say that the h of z converges for mod z greater than 0. So the ROC of h of z is mod z greater than 0. Now let us consider another problem, as per which it is given that there is a signal x of n whose z transform is x of z is equal to log of 1 minus z inverse, and it is also given that the ROC is every z except 0. We have to find x of n. We know that log of 1 minus x can be expanded as minus x square by 2 minus x cube by 3 and so on. From this, x of z can be written as minus z inverse minus z power minus 2 by 2 minus z power minus 3 by 3 and so on. So which can be represented in the summation form as minus sigma n equal to 1 to infinity 1 by n into z power minus n. From this, we can write that the signal x of n is minus 1 by n multiplied by u of n minus 1. So this is the signal x of n from the given x of z and ROC. Here we got the x of n by using the power series expansion. Let us consider another problem, as per which z transform of a signal x of n can be given as z by z minus 2, and the corresponding ROC is mod z greater than 2. From this, we have to find the z transform of n into x of n, the z transform of x of minus n, the z transform of x of n minus 2. Now let us consider the first one, as per which we need to find the z transform of n into x of n, which becomes minus z into d by dz of x of z. This is equal to minus z multiplied by d by dz of z by z minus 2. This upon simplification becomes minus z multiplied by z minus 2 whole square z minus 2 into 1 minus z. This is equal to 2z divided by z minus 2 whole square. Also, the ROC remains as mod z greater than 2 itself in this case. In case of the second one, the z transform of x of minus n is given as x of 1 by z and the ROC becomes 1 by r. From this, we can write that the z transform of x of minus z is 1 by 1 minus 2z and the corresponding ROC is mod z less than 1 by 2. Now let us find out z transform of x of n minus 2 as per the third subproblem. But from the properties of z transform, this is equal to z power minus z minus 2 multiplied by x of z. This is equal to z inverse divided by z minus 2 and the ROC from this is mod z greater than 2. So we have found the required z transforms based on the given x of z. Now let us consider another problem as per which it is given that the system function of a LTI system is h of z is equal to 1 minus 1 by 2 z inverse divided by 1 minus 3 by 8 z inverse plus 1 by 32 z power minus 2. There are three statements given as related to ROC of x of z. The statement 1 is that the system is stable and causal for mod z less than 1 by 4. The second statement is that the system is anti-causal for 1 by 8 less than mod z less than 1 by 4. As per the statement 3, the system is non-causal and unstable for mod z less than 1 by 8. We have to find out which of these three statements are correct. From the given data, we see that the system function can be written as h of z is equal to 1 minus 1 by 2 z inverse divided by 1 minus 1 by 4 z inverse multiplied by 1 minus 1 by 8 z inverse. So the possible ROCs are mod z less than 1 by 8, 1 by 8 less than mod z less than 1 by 4 and mod z greater than 1 by 4. In case of the ROC mod z less than 1 by 8, we see that the system is anti-causal, non-causal and unstable. So the statement 3 is correct. In case of second ROC, the system is non-causal, non-anti-causal and unstable. From this, we see that the statement 2 is not correct. Also, in case of third ROC, the system is stable and causal. But please note that the statement 1 doesn't correspond to a possible ROC of the system as the ROC mod z less than 1 by 4 contains the pole 1 by 8. From this, we see that the statement 1 is also not correct. So here we see that mod z less than 1 by see sorry here we see that the statement corresponding to the mod z less than 1 by 8, that is the third statement, is the only correct statement. Now let us consider another problem as per which the LTI system is described by the difference equation y of n minus 6 into y of n minus 1 is equal to x of n minus 1. If the system is stable, then find the impulse response of the LTI system. From the given LCCDE, by taking Z transform on both sides, the system function can be obtained as h of z is equal to y of z by x of z is equal to z inverse divided by 1 minus 6 z inverse. It's given that the system is stable, so we have to find the corresponding ROCs from the given h of z. From the obtained h of z, the possible ROCs are mod z greater than 6 and mod z less than 6. Mod z greater than 6 is not a correct ROC as the system would be unstable in this case as ROC doesn't include unit circle. So mod z less than 6 is the correct ROC. From this, we can write that the impulse response of the system is minus 6 power n minus 1 into u of minus n. This is because of the reason that z inverse of 1 by 1 minus 6 z inverse for ROC of mod z less than 6 is minus 6 power n u of minus n minus 1. So because of z inverse, the impulse response can be obtained by replacing n by n minus 1. So from this we see that the impulse response of the LTI system is minus 6 power n minus 1 multiplied by u of minus n. Now let us consider another problem as per which the LTI system having impulse response of h of n is equal to 1 by 8 delta of n minus 3 is given an input of x of n whose z transform is given as x of z is equal to z cube minus z inverse plus z power minus 4 by 2 plus z power minus 6 by 3. We need to find the output of the system, that is y of n, at the instant n is equal to 4. From the given impulse response, the system function can be written as h of z is equal to 1 by 8 multiplied by z power minus 3, and the input has a z transform of x of z is equal to z cube minus z inverse plus z power minus 4 by 2 plus z power minus 6 by 3. From this, we see that the output y of n has a z transform of y of z is equal to h of z multiplied by x of z. This is equal to 1 by 8 minus 1 by 8 z power minus 4 plus 1 by 16 z power minus 7 plus 1 by 24 z power minus 9. From this, we see that the output at the instant n is equal to 4 can be given as quotient of z power minus 4, which is minus 1 by 8. So from the given data, we see that the output at the instant n is equal to 4 is minus 1 by 8. Now let us consider another problem as per which the system function of the LTI system is given as h of z is equal to z inverse minus 2 phase 60 degrees divided by 1 minus 3 at a phase of 30 degrees z inverse. It's given that the system is causal. From this, we need to pick the correct option as related to the system. The options given are impulse response of the system is real. Option B is system is unstable. Option D is h of minus 3 is equal to 1 by 2. Option C is h of minus 3 equal to 1 by 2. From the given h of z, we see that the possible ROCs are mod z greater than 3 and mod z less than 3. As the system is causal, ROC should be outside a circle, so mod z greater than 3 is the correct ROC and mod z less than 3 is not a possible ROC as the system is causal. So if we consider the option A, we have to check if the impulse response of the system is real. Here we see that the poles and zeros are not in conjugate pairs. So from this we see that the impulse response of the system is complex. So option A is not correct. If we pick the option B, we have to find if the system is unstable. Here we see that the ROC is mod z greater than 3. So ROC wouldn't include unit circle. So from this we can see that the system is unstable. As per option C, we have to find if h of minus 3 is equal to 1 by 2. It is given that the system is causal, so h of n is equal to 0 for n less than 0. From this, we can say that h of minus 3 would be equal to 0. So the option C is also not correct. So for the given causal system with system function of h of z, we see that option B is the only correct option and option A and C are incorrect. Let us consider another problem as per which there is a causal and stable LTI system which is represented by the difference equation beta into y of n is equal to 3 into y of n minus 1 plus 3 into x of n minus 3 into x of n minus 1. We need to find the correct option as related to the range of values of beta. By taking Z transform on both sides of given LCCDE, we get that beta into y of z minus 3z inverse y of z is equal to 3 into x of z minus 3z inverse x of z. From this, we see that the system function can be written as h of z is equal to y of z by x of z is equal to 3 minus 3z inverse divided by beta minus 3 z inverse. From this we see that the possible ROCs are mod z greater than mod beta by 3 and mod z less than mod beta by 3. But it is given that the system is causal, so mod z less than mod beta by 3 is not a possible ROC. So mod z greater than mod beta by 3 should be the correct ROC. But it is given that the system is stable. So from this, we can say that mod beta by 3 should be less than 1. That implies mod beta less than 3. So the correct option would be, so the correct answer would be mod beta less than 3. Now let us consider another problem as per which there is a signal x of n whose z transform is given as x of z is equal to 3z power 4 plus z square minus 1. It is passed through a LTI system of impulse response h of n whose z transform is given as h of z is equal to 1 minus z power minus 2. We need to find the output at the instant n is equal to 2, that is y of 2. So for getting y of 2, obtain y of z as, that is z transform of y of n as x of z multiplied by h of z. From this result, the output, so the at the instant n is equal to 2, that is y of 2 can be obtained as the coefficient of z power minus 2, which upon simplification can be written as 1. So y of 2 would be equal to 1. Now let us consider another problem as per which there is a LTI system described by the LCCDE y of n minus y of 3a by 2 y of n minus 1 plus a square by 2 y of n minus 2 is equal to x of n minus 1. It's given that the system is causal and unstable. Then we need to find the condition on A. From the given data, we see that the system function of the LTI system can be obtained as h of z is equal to y of z by x of z, which can be obtained by taking z transform on both sides of LCCDE. So we get the system function as z inverse divided by 1 minus 3a by 2 z inverse plus a square by 2 z power minus 2. Here we see that the poles of the system function are at a by 2 and a. From this we see that the possible ROCs are mod z less than a by 2 less than mod z less than a, and mod z greater than a. Here we see that mod z less than a by 2 is not a correct ROC, as the system would be anti-causal in this case. Also, a by 2 less than mod z less than a is also not a correct ROC, as the system would be non-causal in this case. So, but so from the ROC mod z greater than a, we see that the system is causal. So this could be a correct ROC. But it's given that system is unstable. So in this case, sorry, there should be a mod here as well. So in this case, the mod A should be greater than 1. So from this we see that if the system is causal and unstable, the condition on A is that mod A greater than 1.